Hi guys, good evening. I am Ilangovan, online X.com personal for teaching zoology. So we started the molecular basis of inheritance, the structural aspects of the nucleic acid molecules, and also the packaging of DNA in the case of prokaryotes and also in the case of eukaryotes. And what do you mean by nucleosome? We talked about in the last class and discussed also. You know that one a nucleosome is normally formed of a histone octamer plus a DNA. A negatively charged DNA molecule is normally wrapped around the histone protein to form the nucleosome. Simply we can say nucleosome is actually formed of histone protein plus, that is the nucleic acid, the DNA. So it is considered as that one the fundamental packaging unit in chromatin. Packaging unit of chromatin. So the chromatin is nothing but thread-like structures found in the nucleus. So normally the nucleosomes are formed as beads on a string structure in the chromatin. And that chromatin is condensed to form, somehow you know that one, it is actually to form the chromatin fibers. And these chromatin fibers at the time of cell division during metaphase very much condensed and further coiled to form the chromosome. That is the arrangement, nucleosome on a chromatin, forming the chromatin fibers. The chromatin fibers become condensed together and coiled further together to form the thick chromosomes during cell division at the stage of metaphase. We have talked about in the last class. Now in the nucleosome, if we are taking the DNA molecule, nearly about you have 200 base pairs are formed, 200 base pairs. So in a normal individual, so in a normal cell, we have the packaging of chromatin consists of simply the chromatin, then plus nucleosomes, along with that one other components within the nucleus. But in higher level, at higher level of organisms, normally the packaging of chromatin requires another set of proteins or some special set of proteins. And these proteins are also responsible for packaging of chromatin to form the chromatin fibers later on formed to chromosomes. That is at higher level. Such proteins, which are normally found in the case of higher level of organization, are nothing but non-histone chromosomal proteins. So other than histones, also taking part in the formation of nucleosome, helping in the packaging of chromatin. So the packaging of chromatin normally condensed together to form the chromosomes. In the chromatin only we have the beads on a string structure. Made up of you have the proteins histone plus nucleic acid. But at the higher level of organization we have some additional proteins also formed for the packaging of chromatin. They represent non-chromosomal, that is non-histone chromosomal proteins other than histone. Simply they are called as NHC protein, non-histone chromosomal proteins. I mentioned earlier, in a nucleosome, if we are taking the nucleic acid DNA, there are about nearly 200 base pairs are formed just in a DNA bit, which forms a part of the nucleosome. So from which we can calculate, from this unit we can calculate how many base pairs are formed in what is called just in a mammalian cell. So normally, or we can say how many nucleosomes are found in a mammalian cell. So the problem is related to how to calculate the number of nucleosomes in a chromosome in the case of a mammalian cell. So here is the problem, calculate the number of nucleosomes in a mammalian cell. So I mentioned earlier, approximately, just to be the number of base pairs in a nucleosome is about 200. We already knew the number of base pairs in a mammalian cell, including human being, is about 6.6 10 power 9 base pairs. This is a total number of base pairs. But in the case of nucleosome, the number of base pairs would be 200. So from these two values, we can calculate approximate number of nucleosomes formed in a what is called a mammalian cell. So we are taking the total number of base pairs in a mammalian cell divided by the number of base pairs formed in the nucleosome. So we can get approximately 3.3 10 power 7 nucleosomes in a mammalian cell. 3.3 to 10 power 7 nucleosomes. As we have approximately 200 base pairs in a nucleosome, And we know that the total number of actually the base pairs in a mammalian cell, including human beings, is about 6.6 into 10 power 9 base pairs. So we are getting the total number of nucleosomes in a mammalian cell is about 3.3 into 10 power 7. We already knew that the length of the nucleic acid in human being is about 2.2. We have already calculated the total length of a just actually nucleic acid is about 2.2 meters in terms of meters, or in terms of centimeters, you know, the 20 centimeters, or in terms of millimeters, just 2200 millimeters, like that we have. So in such a long, that is 2.2 meters of nucleic acid of DNA, we have about nearly 3.3 into 10 power 7 nucleosomes. That is the total number of nucleosomes in a length of 2.2 meters of DNA. Now, so when you are talking about the chromatin, the thread-like structures, the one which can be stained, there are two different types of chromatin fibers we can find in a chromosome inside the nucleus, or we can find just the interface nucleus. We have two different types of chromatin. One type of chromatin is called euchromatin, another one is called heterochromatin. So what is the main difference between these two? Suppose you are taking the interface nucleus. Now these are all the chromatin fibers. At some regions we have the chromatin fiber is very much dense, darkly stained. So in another region it is in a diffused form, not actually stained dark, very light in nature, in a diffused manner. So accordingly we can have two different types of chromatin. Now the loosely packed region of the chromatin is called what is known as euchromatin. Now this is euchromatin. The densely packed chromatin fibers is called heterochromatin. So the loosely packed chromatin, normally the fibers, or simply we can say chromatin formed during the interface nucleus is called what is known as euchromatin. The densely packed chromatin is called what is known as heterochromatin. While we are applying the staining procedure, so normally this euchromatin just normally stained light. It is stained light just in prophase stage, while the cells are stained with a particular stain, hematoxylin stain, then what will happen? They are stained light. But in the case of heterochromatin, they are stained dark. While stains are applied, the drugs are applied, they become dark. So loosely packed, densely packed, and then light stain and then darkly stain. And which of these two is genetically active or transcriptionally active? So the euchromatin is transcriptionally active, having the ability of just actually transcribing the gene to form the mRNA. So the euchromatin is transcriptionally active, having the ability of just producing mRNA by transcription process. So the message has been transferred in order to translate it to form the protein. But in the case of heterochromatin, it is not genetically active. That means we can say they are not genetically or transcriptionally active. So the transcription process is somewhat actually suppressed because of very much condensation of the chromatin fibers in the case of heterochromatin. So it is transcriptionally active and that one is transcriptionally inactive. Then some more differences. Suppose you are taking the amount of DNA in these two cases. As you see that what it is lightly stained and diffused in nature. That is why it contains only lesser amount of DNA. So in the case of euchromatin, the amount of DNA present is comparatively less or relatively less. But here in the case of heterochromatin, it is formed because of the chromosomal coiling. So we have the combination of many chromatin fibers, so the amount of DNA is much higher. So the amount of DNA in this region is relatively high and here it is relatively less. Then regarding the chromosomal coiling, so the coiling of the chromosomes occurs, that is why you have the heterochromatin region becomes more denser. So the coiling of chromosomal threads, see that one, relatively high. That is why it becomes darker or darkly stained. And the coiling of chromosomes in the case of euchromatin is lesser, that is why it is in a diffused state. So these are some of the differences between euchromatin and heterochromatin. Of these two, the one which is genetically active is nothing but euchromatin. The one which is normally not genetically active, I am saying the word that is what is called genetically active, that is normally the message has been transcribed. So, in the case of euchromatin, the message found in the gene or chromosome or chromatin has been transcribed to form mRNA, but the message in the case of heterochromatin region cannot be transcribed. That is why they are not transcriptionally active. So, there is a main difference between that is euchromatin, heterochromatin, what you observe during the interphase and also prophase stage. Now, we are talking about the DNA as a genetic material. What is the proof for that one? Who has given the proof? DNA is the genetic material. So to begin with, in 1928, an experiment was conducted to prove the genetic material is DNA. But that person did not know that genetic material was DNA. Something was responsible for the expression of characters, one form to another form, like that. So we need, that what if you say a material is genetic, it should have at least 4 important characteristics. We'll discuss later. For example, replication, stability, then having the ability of undergoing mutation, having the ability of expression of characters. These are all some of the important characteristics of genetic material. Now, and that one is responsible for the transmission of characters. And one person by name, Frederick Griffith, doctor by name Frederick Griffith, in 1928 conducted experiment in one bacterium, what is called Streptococcus pneumoniae or Diplococcus pneumoniae, the one responsible for causing the fever pneumonia. You know that one pneumonia is nothing but a kind of bacterial infection. So actually he did experiments to find out something for the treatment of pneumonia. But accidentally he got some other information regarding the genetic material as DNA. So he conducted experiment in the bacterium by name Streptococcus pneumoniae, and those people affected with this this bacterium has developed pneumonia fever. He conducted experiment in the case of mice, and the name of the experiment was transforming principle or transformation experiment. So what is the meaning for that one? So he conducted a number of experiments, a series of experiments in the bacterium Streptococcus pneumoniae, and found that a living organism normally had changed from its one form into another form. That is why it's called as transformation. So when a physical structure of one form has been changed into another form, that phenomenon is called transformation. One form into another form. One just bacterium or living organism have been changed into another form. That was the actual proof he got it. So a living organism had changed in physical form, and that phenomenon is called transformation. One form of bacterium had been transformed into another form. That is why the experiment is called transformation experiment. The principle also called as transformation principle as proposed by Frederick Griffith in 1928. So he conducted experiment on mice. What was the experiment? So in that bacterium he observed 2 different types of bacteria, 2 different types of strains. One type of strain is called 3S strain. 3S strain. That strain is normally virulent. You know the meaning of virulent. A virulent organism is the one which is highly harmful and causes disease. So in contrast to virulent, we have non-virulent or avirulent organisms, and those which do not cause disease are called avirulent. So in that bacterium he observed 2 different strains. One is called 3S. It is virulent because this one actually, this is called S strain. First of all, I would like to say why is it called S strain. So it is called S strain because it produces shiny smooth colonies. So number of bacteria being produced, and all these bacteria have outer coat. When all these are all aggregated together, that gives a smooth colony. So they have a smooth coat. So they have what is called smooth polysaccharide mucus coat. They have simply a mucus coat. The mucus coat is formed of a polysaccharide. That is why they are called smooth strain. So around the cell wall, a mucus coat is released. That mucus coat is giving a shiny color to the bacterium, shiny nature to the bacterium, and also when all aggregated together to form a smooth colony. So that's why it's called as 3S strain or 3S strain. Why is it called as virulent strain? If a mouse is infected with this S strain bacterium, The mouse dies because of the pneumonia infection. As it causes pneumonia and causing the death of the organism, it is called as a virulent strain. So another strain is normally 2R strain. 2R strain. The previous one 3S strain. Another one 2R strain. So R stands for rough colon. As the bacterium doesn't have an outer mucous coat which gives normally slimy nature, smooth nature to the bacterium is absent. That is why it's called as rough strain. When all these bacteria accumulated together, they produce a rough colony. And also this bacterium, this strain doesn't cause normally the pneumonial infection, so that there is no death of organism occurs even though the organism is infected with this R strain. That is why the R strain is called non-virulent. Non-virulent. So bacteria infected with the R strain do not develop actually pneumonia. So normally here not bacteria infected with the R strain, simply it is nothing but actually mice infected with the R strain do not develop pneumonia. Mice infected with the R strain do not develop pneumonia. That's why it's called as avirulent. So there is a meaning for that one. What is the meaning for virulent and avirulent? Virulent one causes infection, pneumonia, and leads to the death of the organism. Non-virulent or avirulent, though infected with that bacterium, namely the R strain, and there is no death of the individual, that is namely the mouse, that is why it's called avirulent. So first one, he did 4 sequence of experiments. So in the first stage, he injected the S strain into the body of the mice. Immediately mice died. The reason for the death of the mice, the mucous polysaccharide coat is acting as a toxin or antigen that causes the death of the mice. So S strain, mainly the mucous coat or the polysaccharide coat, is acting as a poison or a toxin responsible for the death of the mice, because that polysaccharide coat produces pneumonia in that mouse. Then again in the second stage, he injected the R strain into the body of mice. There was no death observed in the case of mice. The mice were living. The reason for that one, that R strain doesn't have the mucus coat, the toxin or the polysaccharide coat, the one which is responsible for the development of pneumonia. That is why even though mouse was infected with this R strain, there was no development of pneumonia as there was no mucopolysaccharide coat. So there was no death of the mouse. The mice were living without any infection. So these were the 2 stages. 1, a strain injected, the mouse dies. 2, R strain injected, normally there was no death of the mouse. And actually the third stage, he was able to kill the bacteria, particularly the S strain, by heating method. While the S strain is heated, what will happen? The outer cellular wall and other structures disintegrate, and only the genetic material were left alone. Only the genetic materials were left alone. All other materials of the what is called S strain disappear. So Griffith was able to kill bacteria, particularly what bacteria? The S bacteria, by heating them. He observed that what will happen when this heat till a strain was injected into the body of mouse. What will happen? There was no death. There was no death. So because in that bacterium, while we just treated the bacterium with a hot temperature, what will happen? The cell wall, the mucous coat, the cytoplasm, all materials disintegrated. As the DNA is highly stable, so it had tolerated the high temperature, the treatment. That is when the DNA was alone there, all other materials disappeared. That is why when that heat kill strain of S was injected into the body of mouse, the mouse alive, the reason for that one, there was no mucus coat to cause the death of the organism, because the mucus coat alone is responsible for causing the death as it is acting as a toxin. Now in the third instance, so this is the third instance. Now the fourth instance, so the first instance, he injected the S strain. The second, he injected the R alone. The third, he killed the S bacterium. The heat killed S strains are now injected the body of mouse, and nothing would happen. The death of the organism doesn't take place, the animal is surviving. So in the fourth instance, he injected a mixture of heat kill, S strain plus R strain. So in the case of heat kill, we have only the genetic material alone. No cell wall, no cytoplasm, no mucus coat. Now in the case of R strain, we have all the structures are being present. Cell wall, but without mucus coat. Without mucus coat, we have cell wall, the genetic material. So he incubated the heat kill S strain plus the R strain and injected together into the body of mouse. What would happen in the fourth stage of actually the experiment? The mouse died. What is the reason for that one? So here there was actually the development of some mucus coat. Something developed in the body of R strain. Now this is the R strain having what is called the nucleic acid and also the outer coat, namely the cell wall. And what will happen here? Something is going on. So during incubation, what will happen with this DNA molecule? Now the DNA of the heat kill S strain entered into the body of this R cell and integrates with the DNA of the R cell. Now this is the DNA of S strain and this is the DNA of the R strain, and it is being taken up, what is called, we can say, transfection process, the uptake of genes by the cells. Then it is called transfection process in the case of animal cells. So here also the genes have been taken up by this bacterium while these two are incubated together. Then what will happen once the DNA of the S strain enters into the R strain cell? It integrates with the R strain DNA. Now we have the genes in this S strain DNA for the synthesis of mucus coat. Now this R strain has the ability of synthesizing the mucus coat. That is why when we inject the heat killed S strain and then R, so before that we have to incubate together for just making the integration or entry of this what is called S strain DNA into what is called the cell cytoplasm and its integration with what is called the recipient cell DNA. So now as the gene for the synthesis of mucus coat is present here, and that one normally synthesizes the mucus coat, as a result now the R strain has been transformed into S strain, has been transformed from non-virulent to virulent state. This is the mechanism. Why? Now why? What is the death? What is the reason for the death of the rat? While we inject the heat kill S strain along with R strain, this is the live one and this is what is called a heat kill dead one. So what is the need and what is the reason lying behind it for the development of a strain which can cause the death of the mouse? This is the reason. So while we are incubating the heat kill S strain DNA plus the entire R cell, now the DNA in the medium has been taken up by this R cell, and the DNA of the S strain integrates with the R cell DNA, and now we have the gene for the synthesis of mucus coat, and that one synthesizes the mucus coat. Now the mucus coat has been developed in the case of R strain. As a result, now the R strain has been transformed into S cell type, and so that it becomes virulent. This is the mechanism operating what we have. Now let's see. So he was able to kill bacteria by heating them. And he observed that the heat kill S strain injected to mice did not kill them. What I say? Because it didn't have, that is a mucus coat, the toxin was not available. And in the fourth instance, what I mentioned, just when he injected a mixture of heat kill S and then the live or bacteria, the mice died. The reason? So from the dead mouse, he also recovered a number of S cells. So we injected only the S strain DNA, heat killed. Once heat killed, we have only the DNA, no other components. But after, as soon as actually the mouse has been dead, he recovered not only just, he recovered cells. The cells are of what is called S type. Previously there was no injection of S cells. We injected only the S DNA along with R cells. But after the death of the organism, he was able to recover some S cells from the dead mice. That means the R cells have been transformed into S cells. Now, what was the conclusion? So, you see that one S strain when injected into the body of mice, the mice line. When S strain heat kill is normally allowed to inject along with R strain, the one which is a living cell. So, what will happen? The mice die. The reason for that one, the transformation principle. So, the following conclusions have been made. So, this is the illustration showing that Grips transformation experiment. So, when we inject the rough strain, you see that one, the mouse lives. And when we are injecting the smooth strain, the mouse dies. When we are injecting the heat kill smooth strain, there is no death for the mouse, it arrives. And when we are injecting the rough strain along with the heat kill smooth strain, then the mouse dies. The reason, because of certain principle that entered into the what is called R cell, converting the R cell into S cell, and that one can produce the mucus core, and that was responsible for the death of the mouse. Now, what is the conclusion? So, he concluded there are certain substances. What substances? Those needed to produce the mucus core, what I mentioned earlier. So, there are certain substances which are needed to produce the mucus core was passed from which cell? The dead cell, the dead bacterium, maybe the R strain, to the live R strain when they were incubated together before they are being injected into the body of mouse, so that the R strain became transformed. So, S strain has been converted into oxide. Actually, to begin here we have the R strain. The S strain DNA has been injected here because of what is called just intake of the genes by the R strain while both are incubated together. So, what will happen? The R strain has been transformed into S. The R strain, which is originally normally non-virulent, has been transformed into S strain, a virulent strain. So, from this one, he also concluded that there are some transforming principle from the body of what we have the dead, just what we can say heat killed dead strain, heat killed strain, or simply heat killed strain and heat killed dead strain, S strain, and that one enabled this R strain to synthesize the mucus core. What I mentioned already, the genes have been incorporated with the genes of R strain, or we have the DNA from the S strain entered in the bacterium of R strain and integrate with the DNA of the R strain. Now the R strain has the capability to synthesize the mucus core. So that principle, some transforming principle, means something was responsible for converting the R strain into S strain. That process called transformation from one form to another form. Changing of one form into another form. Here R form has been transformed into S form. So that is why there are certain transforming principle normally from the heat killed S strain had enabled that is what is called the R strain to synthesize the polysaccharide mucus core so that they become transformed. This is what happened. So this is what happened, nothing but actually this is due to the transfer of some genetic material. He didn't know whether it was DNA or RNA or anything else. Some genetic material was responsible for transforming the R strain into S strain while we conducted the experiment. So he thought like that only, but the characterization of the genetic material was not known. What was the genetic material that was transferred from what is called this S strain to the R strain, responsible for converting the R strain to S strain? That was not known. So later it was normally known as the genetic material, the DNA. So he did not know actually the biochemical nature of the genetic material. So for that, three people, they did what we call this one, the biochemical characterization of transforming principle, whether it was DNA or RNA or protein. That is called biochemical characterization of transforming principle. So three different people, because Griff didn't know the characterization, the biochemical characterization of the genetic material. Simply he thought that some transforming principle from the S strain entered into the R strain and then converting the R strain into S strain so that it can synthesize what is called the mucopolysaccharide, or simply the polysaccharide, the mucus coat. So three different people, one Oswald Avery, Colin McLeod and McLean McCarthy. just between 1933 to 1944. They proved that the transforming principle was none other than the DNA material by means of experiments. They proved that in the case of transforming principle in Streptococcus pneumoniae was nothing but the DNA material. Now, how did they actually prove that one? Now, they just purified biochemicals from the heat kill strain. They just collected, they purified the DNA, purified the RNA, purified the proteins from the S strain. So the heat kill S strain, they purified it. They obtained the various biochemicals from the body of that killed S cells like proteins, RNA and DNA. So in order to find out which could transform the R cell into S cells, which is the transforming principle, whether the RNA or the protein or the DNA, for that they have actually purified. So by means of centrifuge method, they purified the protein, they collected the proteins, the RNA and DNA molecules from what is called the heat killed S strain. And from these purification methods, they were able to know that only that is the DNA from the S bacteria had caused the transformation of the R strain into S strain. R strain into S strain. So after purification. So further they treated the cells. For example, in the case of that is S cells or the R cells, and they did some experiments. What experiment? So normally you know that one we have the enzymes which have the capacity to digest specific substrates. And in the first instance, actually they introduced the protein digesting enzymes into the S cells or the R cells. After that experiment gets over, they injected the protein digesting enzymes into what is called the transformed cell. And that one not or when they culture these R cells, S cells along with the protein digesting enzymes, what will happen? The protein digesting enzymes did not inhibit, did not affect the transformation process. Because when we introduced the protein digesting enzymes, it may digest all the proteins formed in the cell. And even though the proteins are digested, the transformation occurred, so they thought that it was not protein. Similarly, they also just treated the cells with what is called RNA digesting enzymes, RNAs. And that one also did not affect the transformation process. The process was going on. Nothing would happen. So it never stopped. So even though the RNA was absent because of the digestion, the transformation had occurred. The R cell had been transformed into S. So from this experimental analysis, they just came to know that the RNA or proteins, they were not the genetic material, because the transformation principle or the transformation process was going on even though the proteins or the RNA in the cells had been affected or had been damaged or had been digested by using the enzymes. And also the next stage, they treated the cells with the DNA-S, the deoxyribonuclease enzyme. So when they actually treated the cells with the DNA-SE, what is called deoxyribonuclease enzyme, it is responsible for the breakdown of nucleic acid. So when the cells are treated with this DNA-SE, the enzyme, what will happen? It affected the transformation process, because that enzyme had the ability of digesting or breaking down the nucleic acid. Once the DNA had been broken, damaged or digested with the help of this enzyme, so as it was the major source for the transformation process, no transformation process occurred. So when the cells were treated with the protein, nothing would affect the transformation process. When the cell was treated with what is called the RNA digesting enzyme, nothing would happen. Protein digesting enzyme, RNA digesting enzyme, nothing would affect what is called the transformation process. When the cells were treated with normally the deoxyribonuclease enzyme, the one responsible for the breakdown of nucleic acid, then that process, the introduction of nucleic acid enzyme for digestion of DNA had affected the transformation process. No transformation occurred. So from that it was evident that the transforming principle was none other than what is called DNA. So these were the experiments conducted by the three people to prove that the DNA was the transforming principle in the case of the bacteria. But the DNA as a genetic material in all the organisms have been proved by two people in their experiment by means of what is called transduction experiment in bacteria. So, Avery, then McLeod and McCarthy, they proved that in bacteria the transforming principle was DNA. But they did not explain that DNA is a genetic material universally in all the eukaryotic organisms. Now the DNA is a genetic material in all the organisms have been proved by two different people, Alfred D. Hershey and Martha Chase. These were the two people in 1952 experimentally proved that the DNA is a genetic material in all the eukaryotic organisms and also in bacteriophages, etc. What was the name of the experiment? They conducted the translation experiment in the case of bacteria. You know the meaning of translation process. So translation is a process in which a piece or whole DNA segment from one bacterium, that is namely the donor bacterium, has been transferred to another bacterium, namely the recipient bacterium, through or via a vector. The vector is nothing but a bacteriophage. So if any genetic material transfer occurs from one bacterium to another through a bacteriophage, then the phenomenon is called translation process. So having the ability of transfer. So here the bacteriophage is acting as a vector. So they followed the same principle, what is called the translation experiment, by using the bacterial virus, the one which attacks the bacteria, to prove that DNA is a genetic material in all the eukaryotic organisms. And that experiment is called Alfred Hershey and Martha Chase experiment, to prove that DNA is a genetic material. So the name of the experiment, translation experiment, that is what is called in bacteria. You know that one, if any bacteriophage is attached to the bacteria, it injects its DNA into the bacteria, then what will happen? The DNA of the virus integrates with the bacterial DNA and replicates along with the bacterial DNA to produce multiple copies of virus particles. This is what is happening. So we have lysogenic cycle, lytic cycle, you know that one. When a bacterial virus or bacteriophage affects or attacks or just actually causing damage to the bacteria, then what will happen? We have two types of cycle, lytic cycle and lysogenic cycle. We are not going to talk about this one. So normally the bacterial virus, when attaches to the bacterium, first it injects its genetic material, leaving its protein coat outside. Then the DNA of the virus integrates with the bacterial DNA and replicates along with the bacterial DNA to produce multiple copies of virus particles. And they are following this principle for just proving the DNA as a genetic material. And for that, actually, they did experiment. So, why they worked together? So, they worked to discover whether it was protein or DNA that entered in the bacteria and caused transformation. Whether it was the genetic material, namely the DNA, or protein that entered into the bacteria from the bacteriophage. So whether it was protein or DNA from the viruses that entered in bacteria, and how far the materials have been transferred, how transferred, and they proved only it is DNA that entered the bacteria and not the protein. And the DNA only integrates with, you know that one, while the bacterium being attacked by the bacterial virus. So the bacterial virus, the bacteriophage, attaches itself to the surface of the bacterium, introduces only its genetic material, not its protein coat. And the DNA only enters into the bacterial cell, and that is the proof given by them. So they worked together to discover whether it was a protein or DNA that entered into the bacteria. And that is why they did the experiment, the transaction experiment. Further, they cultured some viruses in a medium. There are two media that took together. One medium contains radioactive phosphorus. One medium contains radioactive phosphorus. So they culture the virus particles, many virus particles in a medium with what is called radioactive phosphorus P32. In another medium, they culture the virus particles in a medium, the one which contains what is called radioactive sulfur, sulfur 35. So in one medium we have what is called radioactive phosphorus, another medium we have sulfur 35, both are radioactive. So they cultured viruses in two different media. Some viruses in what is called phosphorus 32 or just P32, and another medium containing what is called S35. So both are radioactive. So those viruses, what is the main purpose? You know that one, if you are taking the phosphorus, phosphorus is found only in DNA, not found in protein. And if you are taking sulfur, sulfur is found only in protein, not in DNA. That's why they took sulfur and phosphorus. So phosphorus found in DNA and sulfur is found only in protein, but not in DNA. And similarly, phosphorus is absent in protein. That is why they took these two radioactive isotopes. So when the virus is grown in the presence of radioactive phosphorus, they become radioactive because the radioactive phosphorus is incorporated in their DNA molecule. So the viruses cultured or grown in a medium with radioactive phosphorus become radioactive. Now the radioactive phosphorus has been incorporated in the DNA of such virus particles. But that just what is called the radioactive phosphorus was not present in protein, because you know that one, there is no phosphorus in protein. That is number one. So viruses grown in the presence of radioactive phosphorus contain radioactive DNA, because it becomes radioactive, the DNA in which the phosphorus had been incorporated, but not radioactive protein. So we don't have radioactive protein because in protein molecule there is no phosphorus. Because DNA contains phosphorus, I mentioned already, proteins doesn't. Actually the protein doesn't. Then in another medium, so you see the viruses, similarly the viruses which were grown and which were cultivated in a medium having what is called radioactive sulfur. These viruses contain radioactive sulfur in their protein coat and not DNA. So viruses grown in a medium with what is called radioactive sulfur, they contained sulfur in proteins. So the protein normally became radioactive, but not the DNA, because in the DNA sulfur was absent. So they have radioactive protein but not radioactive DNA, because DNA does not contain what is called the sulfur. And now what we have? We have two sets of viruses. One virus with the radioactive phosphorus or one virus with the radioactive DNA. Another virus or set of virus having what is called radioactive protein, that is in their protein coat. Now they are allowed to infect the bacteria. So now they are attaching themselves in different groups of bacteria, they are culturing. So in one medium they are allowing the bacterium with the viruses having radioactive protein, and another medium having bacteria along with a virus having what is called phosphorus, radioactive phosphorus. That is what is having, they have DNA with phosphorus, radioactive phosphorus. So two different media, one medium with bacteria with sulfur containing protein, what is called the virus particle, and another virus, another medium having the bacteria with the virus particles, and those virus particles contain radioactive DNA because of the presence of phosphorus. So what will happen? So now the infection proceeds. While the infection proceeds, we have that they were able to isolate, they were able to remove the protein coat by means of what is called agitating them in a blender. How far they were able to isolate the protein coat from the bacteria. You see that one, this is the bacteria, now we have the bacteriophage attached to it, this is the protein coat. So only the DNA enters here, now the protein coat is left out, and that protein coat is normally removed from the bacterial surface by means of one process, by agitating them in a blender. That is a method by which. So the virus particles were also separated from bacteria. So now we have agitated them, so the virus particles, namely there is a virus protein coat and the bacteria gets separated, and they are by means of what is called blending process. Now we have to isolate the virus particles alone, and for that, and these are all subjected to what is called centrifuging. By spinning them by means of centrifuge method, we have to what is called separate the virus particles. So now this is the attachment. By first process, we are just removing the protein coat. By second process, by centrifuge method, by spinning them, we have to separate them. This is the protein coat of the virus and this is the bacteria cell. And that is the third process. First one, infection. The second one, agitating them just to separate, what is called to remove or to separate the protein coat. The third one, we have to isolate the protein particles or what is called the virus particles from the bacterial particles, and then you have to analyze it. What is the nature of the bacterium? What is the nature of the protein coat in these two different what is called analysis or culturing processes. Now, number one. So first, actually what would happen? So the bacteria that were normally infected with the viruses that had radioactive DNA became radioactive or they were radioactive. Those bacteria which were grown or which were normally infected with the viruses and those viruses had DNA, now they become radioactive. That means only the DNA entered into the bacterium and not the protein coat. That is why we have that bacteria became radioactive because of the entry of the radioactive DNA from the virus particle into the bacteria, and it integrates with the bacterial DNA and multiplies or replicates along with the bacterial DNA. Now the resultant cells, the bacterial cells, are all radioactive because they contain in them the radioactive phosphorus. So from this experiment, actually, see that one, it is normally confirmed that it is only the DNA that entered the bacterium and not the protein. And second, the bacteria that were infected with the viruses that had radioactive proteins were not radioactive. So the bacteria that were infected with what is called the radioactive, that is virus, the radioactive virus, that is viruses that had radioactive protein, and that one viruses with the radioactive DNA. The second case, bacteria that were grown along with the viruses that had radioactive protein were not radioactive. The meaning for that one, the protein coat or the protein never entered the bacterial cell and never integrated with the DNA and never replicates along with the DNA. That is why these cells are not radioactive, and those bacterial cells just grown or infected with the viruses which had radioactive DNA became radioactive because of the entry of DNA, and those bacteria which were grown or which were infected with the viruses which had normally radioactive protein will not be radioactive. So from these two separate experiments, and they were able to conclude that normally the proteins did not enter into the bacterial cells. It is only the DNA that enters into the bacterial cell and the protein coat of the virus remain outside. So from this experiment they were able to actually conclude that it was DNA alone that entered into the bacterial cell, and that also the DNA is acting as a genetic material during the transmission process of characters. Now here is actually the diagrammatic illustration. So on the left side, see the virus was grown in a medium having what is called radioactive sulfur. That is what is called as radioactive sulfur-laden protein capsule, because the sulfur is incorporated only in the protein coat and not incorporated in the DNA when viruses were grown in a medium with radioactive protein. Then in another medium we grew, you know that one, that medium contained radioactive phosphorus, so that now this virus contains the DNA with radioactive phosphorus, because phosphorus found only in the DNA and not in the protein coat. So the infection persists. Now they attach themselves to the wall of the bacterium. Then later we see that one, the DNA material from the viruses enter into the bacteria as a common procedure. You know that one, the bacteriophage injects the DNA into the bacterial cell. The injected DNA then integrates with the bacterial DNA and multiplies or replicates along with it. This is what is happening. Now here I am taking in the left side, now the protein coat with the sulfur. Now here you see that one, the DNA is injected, the DNA is not radioactive. And here now we receive the cells. The cells are not radioactive, the bacterial cells are not radioactive, because they did not have the DNA with the sulfur or with what is called anything else. So we use only just what we have the sulfur only. But the supernatant, the protein coats, you see that one, the protein coats were still with what is called radioactive sulfur. That means the sulfur is incorporated in the protein coat, and that is not entered into what is called, that is a cell. And that is why they are called the supernatants. They have only the protein with the sulfur, or what we call the radioactive sulfur. Now these cells, the resident cells, normally not radioactive, because here the DNA is not radioactive, the injected DNA is not radioactive, that is why the cells also not radioactive, but the protein code radioactive the sulfur. Now in the second experiment we have the virus particles having what is called radioactive phosphorus, which is normally called as radioactive P32 labeled DNA. Now infection, it injects the DNA. Now the DNA integrates with the bacterial cell DNA and multiplies or replicates along with the bacterial cell DNA, so that we have received a number of bacterial cells with radioactive phosphorus. So that is why we have normally the cells. These cells are considered as radioactive cells. The bacteria with the radioactive property, because they have radioactive DNA. So the supernatant did not have any what is called the phosphorus, because phosphorus the protein code normally doesn't contain any just what is called phosphorus. That is why the phosphorus, radioactive phosphorus, is not incorporated in the supernatant. Now the supernatant is free from phosphorus, whereas the bacterial cells were radioactive, because the DNA of the virus already labeled with the radioactive phosphorus entered into the bacterial cells, multiplied, resulting bacterial cells also had just the DNA molecule with the radioactive phosphorus. So from these evidences, from these two experiments, you could see only it is the DNA that entered in the cell and not the protein. And from that it is also evident that it is only the DNA that is acting as a genetic material responsible for the development of such cells, either radioactive cells or non-radioactive cells. So there is a conclusion. So according to them, the DNA is a genetic material in all cases of eukaryotic organisms and also in the case of bacteriophages. So Griffith normally never determined about the genetic nature, whether it was DNA or RNA. Simply he said transforming principle. The transforming principle was identified by DNA by three different people. So Avegi, then McCarthy and McLeod. But the DNA is a genetic material in all the organisms was proved experimentally by Chase and Martha Chase and then Albert D. Hershey. These were the two people in 1952 explained DNA as a genetic material by using the experiment what is called the transduction in bacteria. Now what are the properties of genetic material? So you know that the genetic material has its own property, either DNA or RNA. And if you take for example the plant viruses, many plant viruses excepting one or two viruses, and some animal viruses, for example the TME, the tobacco mosaic virus, and animal viruses, measles virus, okay, and also one bacteriophage, what is called QB bacteriophage. So in these normally virus particles, we have RNA as a genetic material. So almost all the plant viruses, except I am giving here, for example, cauliflower mosaic virus and Dahlia mosaic virus. In these two cases, we have DNA. So all plant viruses excepting these two. Then almost all animal viruses. There are exceptions. So for example, the pox viruses, they have DNA. So the animal viruses. And you know that all bacteriophages contain DNA excepting this QB bacteriophage. Excepting the QB bacteriophage. So the QB bacteriophage alone contains the DNA and all other bacteriophages, alone contains RNA and all other bacteriophages contain DNA. So number one, what is the genetic nature? It may be RNA. For example, plant viruses, animal viruses, and then QB bacteriophage. Or it may be in the form of DNA. So DNA is a genetic material in almost all the eukaryotic organisms, all bacteriophages, some animal viruses like pox viruses, a few plant viruses like cauliflower mosaic virus and also Dahlia mosaic virus. In these two cases, we have DNA as a genetic material, an exemption when compared to other plant viruses. So, in the case of pox viruses, actually we have DNA. Even in the case of hepatitis B virus, it contains DNA. An enveloped virus causing what is called jaundice liver carcinoma also contains DNA as a genetic material. Don't forget this one. Then what are the other characteristics? Suppose we are assuming a material that is genetic in nature. So they should exhibit 4 important properties. What are the 4 important properties of a genetic material? We will consider them as genetic material only when they have these properties. So any genetic material has the following 4 properties. It may be either RNA or DNA. Number 1, replication. Number 2, stability. Number 3, mutation. Number 4, expression. So they should have all these 4 properties, then only we can consider them as a genetic material. It may be either DNA or RNA. Now let's take what is called replication. And a genetic material should have the ability of producing its own copy or replica by a process what is called replication process. Now this replication process is exhibited both by DNA and RNA. It is common to both the DNA and RNA. They have the ability of replicating their own DNA or RNA copies. So that phenomenon is called replication and it's being exhibited by RNA and DNA. Now stability. So when you are taking the genetic material, it should be both structurally and chemically stable molecule. It should be structurally and chemically stable. It cannot be altered by means of action. Suppose you are taking for example error mutations. Normally we have 10 to 100 million. One error in 10 to 100 million genes occur at DNA molecule or base pairs. So a DNA or RNA should be stable. So normally though RNA and DNA are considered genetic material, of these two, DNA is more stable than RNA. That's why it's considered as the storage of genetic information, as it is more stable. If we are comparing the stability of RNA and DNA, the DNA is more stable than RNA, but that is one of the properties of any genetic material. And for example, stability as one of the properties of genetic material was very evident in Griff's experiment. So we are considering the stability as one of the important properties of genetic material. That was evident also in the first experiment, namely the Griff's experiment as the transforming principle. Oh. So in the transforming principle, we know that he did heat killing of bacteria. When the bacteria were subjected to what is called heat killing process, and the heat killed bacteria did not destroy what is called the genetic material. Only the outer capsule, the cytoplasm and other things disappeared, but the genetic material was stable. So it was very evident in the first principle, also in the first experiment also, that DNA was, or the genetic materials were very stable. That was explained in the transforming principle. It was very evident how, that is, when he killed what is called, when he treated the S strain to kill them, most structures disappeared, but the heat killed bacteria did not destroy any of or some of the genetic materials, some of the or any of the genetic materials possessed by them. So that is one of the stability we can get by means of experimental proof. I mentioned already the DNA is more stable than RNA, and we can give also reasons why DNA is more stable than RNA. So you know that in the case of DNA, the two strands being complemented. If the two strands are subjected to heat treatment, what will happen? They get separated. Even if they are separated, they are coming together once again because of the complementarity, and so that what you infer, they resist changes by evolving them by a process of repair. So repairing of DNA is very easy because of the complementary process. Even though they are subjected to heat treatment for separation, even the two strands are separated, once again they are coming together, and also you see that they have the ability to resist against such changes, and also they are getting repaired once again. By a process of repair, once again they are assembled. That is why they are said to be more stable. The second reason, now if you are taking the reverse sugar, this is what we have just actually. This is position number 2, the second carbon. Here we have the OH group in the case of reverse. But in the case of DNA, we have hydrogen in that second carbon attachment. We have the hydroxyl group, we have what is called the hydrogen group. That is in the case of deoxyribose sugar, this is in the case of ribose sugar. Now this OH group is highly reactive. It is normally catalytic. See that one? OH group present at every nucleotide means that is normally in the second position of the reverse sugar of the reverse nucleotide. It is highly reactive because of the position of this OH group, only the RNA is highly reactive. As a result, this highly reactive group makes the RNA more labile and easily degradable. As it is more reactive, it makes the RNA more easily degradable. This is because of the position of the OH group attached to the second carbon atom of the ribosome. But in the case of DNA, we have the hydrogen group. That is why the DNA is not reactive, hence it is more stable. So normally, if you take RNA, it is acting as a catalytic role. It is having a catalytic role and hence unstable. So for example, some of the, even in the case of bacteria, the rRNA, 23R RNA, which is acting as an enzyme, what is called the ribosome, doing its own catalytic role. So normally the RNA is known to be catalytic, creating some chemical reactions, causing even the breakdown of nucleic acid RNA. Hence they are reactive, and such a reactive nature makes it unstable. So the DNA is chemically less reactive and more stable. That is why it is considered as the most important genetic material for storage of genetic information when compared to the RNA. So DNA chemically is less reactive and structurally more stable than RNA. Therefore, DNA is a better genetic material. And another important feature why normally the DNA is more stable than RNA. So in place of uracil in the case of RNA, in DNA we have thymine. That thymine provides additional stability to the DNA molecule. So the presence of thymine provides additional stability to the DNA molecule. So these are all the factors which make the DNA as more stable than RNA. So number one, we have just the complementarity. Number two, we have normally the OH group in the ribose sugar. And number three, the RNA's catalytic role. That is why it is more reactive. So these are all the three properties which make the RNA less stable than that of what is called the DNA. So the first two properties, one is what is called the replication and the one is stability. The DNA is more stable than RNA. This is because of some characters what I mentioned, the OH group, the complementarity and also the catalytic role of RNA, which make normally the RNA even just not, we can say, less stable, just unstable. But the DNA is chemically and structurally more stable, so that it is being considered as actually the genetic material for the storage of information. But RNA can be used for the transfer of genetic information. So we'll see and we'll discuss more about this one, as it is just actually a topic of heart, and I'll proceed towards this one in the next class as one at a time concluding. And thank you for your cooperation, post your questions. So now the class is completed. Meet you once again. Till then, goodbye.